Hello and welcome back after the break. So hope I am audible as well as visible to you all, right? Just confirm that I am audible as well as visible to you all. Done, 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 done. So we completed biodiversity, biodiversity of India, and certain important aspects associated with the biodiversity perspectives, the acts of 1972, and some rough ideas like the sites and how it is implemented in the context of India, and about the vermin species. And at present, the center is having the authority to declare any species as the vermin. So we made an effort in understanding all those with reference to current affairs as well as basics, the Ramsar wetlands in India, the tiger reserves in India, the elephant reserves, and other aspects. So now we'll move on to understand something called as ozone depletion. Now, before moving down to ozone depletion, first we'll try to understand what is ozone. Then we will move on to depletion part. Then we will move on to the depletion part. Now, the moment when you talk about ozone. So we always have two types of ozone. Always we have two types of ozones are there. The ozone which is found at the ground surface, the ozone which is found near the surface, near surface. It is referred as a pollutant. It is referred as a pollutant. And it creates large amount of disease, respiratory disease, etc. So hence we refer this as bad ozone. Bad ozone, which creates many health hazards. Which creates health hazards, right, near the surface. Then apart from that, we also have a ozone which is found at great height. We also have a ozone which is found at the height. If you take this as a surface, so this region, that is in between 25 to 30 kilometers, 25 to 30 kilometers above the ground, in the second sphere of the atmosphere called as stratosphere. So we have the layer called as ozone layer, and this ozone is referred as good ozone. This ozone is referred as good ozone. And this good ozone, it absorbs the ultraviolet radiations. It absorbs the ultraviolet radiations and us from skin cancer. Protects us from skin cancer. And it also protects us from eyes disease called as cataract disease. Eyes disease, we refer them as cataract disease. Now, when we talk about this ozone which is found here, it is a process which is involved in the formation of this ozone. And this ozone, which is referred as good ozone, is highly unstable gas. It is highly unstable gas. And in this session, we'll try to understand about this good ozone. We'll try to understand about good ozone. So there are two types of ozones. One is the ground ozone, which is found at the surface, and this is referred as a pollutant, which can create large amount of respiratory disease. And the ozone which is found at the height, at around 25 to 30 degrees, is referred as good ozone, which protects us from harmful ultraviolet radiations. Now, when we talk about the ozone here, ozone here, a process is involved here. At the higher altitude, above the earth's surface, ultraviolet radiations of the sun, UV radiations of the sun. They react with the oxygen molecule. They react with the oxygen molecule and breaks the oxygen molecule into oxygen atom. Oxygen atom. Oxygen molecule is broken into oxygen atom. And this oxygen atom, it combines with the existing oxygen molecule and forms O3, which is referred as ozone. Ozone. And once this ozone is formed at height, once this ozone is found at the height, then it is transported downward. It is transported down. And it is found in this layer. That is the second layer of the Earth's atmosphere, called as stratosphere. And this is referred as good ozone, which prevents us from harmful ultraviolet radiations. And the thickness of this ozone, the thickness of this ozone is measured by a unit called as Dobson unit. Dobson unit. Now, the ideal thickness which protects us from ultraviolet radiation, the ideal thickness which protects us from ultraviolet radiation is when the thickness is average 300 Dobson units. So if the average thickness is 300 Dobson units, then it will protect us from harmful ultraviolet radiations. 300 Dobson units. Roughly, when you calculate that, it is somewhere around 3 millimeters. 3 mm. Very compressed ozone type. So this is what ozone which is found in this layer, and it protects us from harmful ultraviolet radiations. And remember, this ozone which is formed is highly unstable. It is highly unstable. It means that it breaks very fast. It dissociates very fast. It breaks or dissociates very fast. Maybe 30 days, 40 days, or 100 days. After that, it breaks also very fast. This is what we refer them as a good ozone. Good ozone. Now, understand something about this good ozone and how it is dissociated. How it is dissociated. So I'm talking about natural process. Natural process. Right. In the natural process, the ultraviolet radiations, they react with the oxygen molecule and breaks the oxygen molecule into oxygen atom, O and O. And this oxygen atom combines with the oxygen molecule and forms the ozone. Forms the ozone. This is how the ozone is formed, and then it is transported downward. And this ozone which is formed is not permanent. This is highly unstable. This is highly unstable. It means that this ozone which is formed after 20 days, 100 days, or 120 days, it dissociates faster. This ozone dissociates faster. It breaks also faster. Breaks or dissociates. It breaks into oxygen and oxygen molecule. So naturally in the Earth's atmosphere, from the oxygen, ozone is formed, and this ozone dissociates and it creates oxygen. It creates oxygen. And this is a cycle which is created by that. A cycle which is created. It is not the one time, it is continuously which is being created. And this cycle was systematically analyzed by an Australian meteorologist called as Chapman. Chapman. And hence, in the honor of Chapman, this cycle is referred as Chapman cycle. Chapman cycle. This is a natural process where the ozone is formed and it is dissociated also. So whatever is formed, whatever is developed is dissociated. Dissociated. And this is where it maintains the ideal thickness. So this maintains the ideal thickness. It is something like this. You are having a water tank. We are having a water tank. Right. So in this water tank, there is a volume of water which is maintained here. The thickness of water is maintained here. Water which is maintained. Now, if there is a 2 liters of water which is added, 2 liters of water you are adding here, and the same 2 liters of water, 2 liters of water is removed. It will not affect the thickness of the water. So the volume of water in the tank will remains the same. So it will not affect the volume of water because whatever is added is removed here. This is how the natural process is there. So ozone formation and dissociation, it is always balanced where it will maintain the ideal thickness. It will maintain the ideal thickness around 300 Dobson units, which protects us from harmful ultraviolet radiation. And this was some 100 years back or 200 years back. 100 years back or 200 years back, which maintained the thickness of ozone. But later we find certain aspects were there. Aspects in the sense, understand that. We found that naturally also, and naturally it is referred as Chapman cycle. If you take the data of the present condition means say 2010, 1950 or 1980s, so somewhere around present, up to 50 years data back. So we started using luxuries like air conditioners, we started using refrigerators, etc. So these air conditioners, refrigerators, etc., so they emitted large amount of gases like chlorine, bromine, chlorofluorocarbons, etc. Chlorine, bromine, CFCs, etc. So they released a large amount of chlorine, bromine, CFCs, and these all are man-made because of using of air conditioners, refrigerators, etc. Right. Now what happens here is this chlorine or CFCs, when they are released in the atmosphere, so they reach to the second layer where the ozone is there. So reach to the second layer where the ozone layer is present, and they react with the ozone layer. Now how they react? Take this CFC, chlorofluorocarbon, right? So this chlorofluorocarbon, CFC, which is released by refrigerators, after reaching to the height, it frees chlorine from that. It frees the chlorine from CFC. So chlorine becomes free from CFC. Now this chlorine which is free from CFC, it will react with the ozone molecule and breaks the ozone molecule into ClO and O2. So this is not the only one time it is does. So once it has broken the ozone molecule, and after this Cl again becomes free. it becomes free. And this chlorine will target the next ozone, and again it will destroys that ozone, destroy that ozone. So in this process, which is continuously being done, one chlorine molecule, one chlorine molecule has the capacity of destroying 1 lakh of ozone molecules. So one chlorine can destroy 1 lakh of ozone molecule. Remember this. This is where we talk about man-made aspect. So here, if you take the present or 50 years back, the formation of ozone has not altered. It is formed in the same manner. It is formed in the same manner. There is no variation in the formation. It is developed in the same manner which was seen some 500 years back. But if you take the dissociation of ozone or breaking up of ozone, so this breaking up of ozone at present we find it is done by two ways. It is done by two ways. The first one is natural way, and the second one is man-made way. Man-made way. That is due to release of the chlorine, fluorine, CFC, etc. That is release of chlorofluorocarbon, chlorine, etc. Release of CFC, chlorine, etc. So because of these two conditions, naturally as well as man-made, naturally as well as man-made. Now this is a condition where we say, the previous example, we are having that tank, we are having the tank, and in this tank, when you talk about the depth of the water is there, and the addition is 5 liters, and the dissociation was 5 liters. That was naturally. This is naturally where the dissociation is done 5 liters. Then we find man-made dissociation is also there. So because of the man-made activities, that has developed one more area where the dissociation is there because of man-made factors. So this dissociation may remove, say, 2 liters of water extra. So if there is a dissociation due to natural factors and man-made factors, so what will happen to the volume of water which is there in the tank? Will it remain the same or it will decrease? Will it remain same or it will decrease? When we find the dissociation is done with natural as well as man-made, so this will decrease. So this will decrease. So the thickness will decrease. And this is what happening in the ozone. So we find the formation of ozone is same, but the dissociation of ozone is done in two ways, that is natural as well as man-made. And because of that, the ozone layer is becoming thin. So it is something like this. The formation of the ozone has maintained the same, but we find the dissociation has increased due to natural and man-made factors. And this dissociation is something which is more than what it is formed, and which is making the ozone layer to become thin. The ozone layer is becoming thin. Now this ozone layer, ideal thickness of ozone layer is average 300 Dobson unit. Now when the ozone layer becomes less than 200, when it becomes less than its thickness, when it becomes less than 200 Dobson units, it means that thinning of ozone layer below the natural process. thinning of ozone layer below the natural process. When it is less than 200 Dobson units, we refer this as ozone depletion. We refer this as ozone depletion. That is, thinning of ozone layer well below the natural process is referred as ozone depletion. Now here, the ozone depletion is due to these two factors, natural and man-made factors. Natural as well as man-made factors. Man-made factors. But here you should remember, this man-made factor is the major contributor. Man-made factor is the major contributors. Major contributor in the context of ozone depletion. In the context of ozone depletion. And the substances which makes the ozone depletion, the substances which makes the thinning of ozones, which are released by man-made activities, like chlorofluorocarbon, chlorine, bromine, etc. We refer them as ozone depleting substances. We refer this as ozone depleting substances, or ODS, ozone depleting substances. And hence CFCs, chlorine, bromine, we refer them as ODS, ozone depleting substances. Is that clear? So this is what we say, thinning of the ozone layer. Thinning of the ozone layer well below the natural process. We refer that as ozone depletion. That is, the average thickness of ozone, which decreases from 300 Dobson unit to less than 200 Dobson units. Then we refer that as ozone depletion. Is that clear? So hence we say ozone depletion is anthropogenic or man-made one. Anthropogenic or man-made, where the ozone layer has become thin. Now, when the ozone layer becomes thin, ultraviolet radiation will percolate and reaches to the earth, which can create more number of cancers, which can create more number of cataract disease, which can affect the biodiversities, So this is the mechanism of ozone depletion. And any areas wherever the ozone depleting substances are more, then the ozone depletion is maximum. It is found in any part. It is found The ozone depletion can be in any part, of the earth. That is, at the equator, at the tropics, and at the poles. So you can find them at the equator, we can find at the temperate region, and we can find them at the poles also. Right. Now this is some rough idea, the aspect of the ozone depletion. Now, a systematic study was done, and generally in the year 1995, three scientists, they proved that the CFC is the major reason for ozone depletion. CFC is the major reason for ozone depletion. And these three scientists were Roland, Molina, and Cruzan. So these scientists, they explained that the CFC is the major culprit because of which the ozone depletion is taking place. And that is the reason why in the year 1995, they received the Nobel Prize in the chemistry section, where they identified that CFC is the major reason for the ozone depletion. Is it clear? Ozone and ozone depletion. And the substances are referred as ozone depleting substances. Ozone depleting substances. So this is some rough idea about ozone and man-made phenomenon. Now, when we move on to a bit complex phenomenon, when we moved on to a bit complex phenomenon, that is the southern hemisphere of the earth, where we refer that as Antarctica. In the southern hemisphere of the earth, where we refer them as Antarctica. Antarctica. This ozone layer in Antarctica, this ozone layer in Antarctica, it becomes so thin, it becomes so thin or thinner. Sometimes it is less than 100 Dobson unit, less than 100 Dobson unit. So when it becomes very thin, less than 100 Dobson unit, practically it is very, very thin, so that the gases can reach to the earth, ultraviolet radiation can reach to the earth. And such thinning of the ozone layer in the Antarctica, we refer that as ozone hole. It is not a hole, practically it is not a hole, it is a thinning of ozone layer less than 100 or below 100 Dobson unit, less than or below 100 Dobson units. And this we refer that as ozone hole, ozone hole. So in the Antarctica, we experience this ozone hole, ozone hole. And this ozone hole in the Antarctica is not haphazard way. It is seen every year, and it is periodic. It means fixed time is there. Fixed time is there. That is, it starts depleting. It starts depleting from the month of August. It starts depleting from the month of August, and the maximum depletion, we refer that as ozone hole, ozone hole. It is found in between the September and October. So maximum depletion is seen between September end or October first week, end of September or first week of October. Maximum depletion takes place. After that, it improves, it improves, and by the month of December, by the month of December, the ozone hole will recover. Every year, the same process is seen. Every year, the same process is seen. That is, it starts from the month of August, the depletion becomes maximum in between September and October, and it recovers by the month of December. It recovers by the month of December. And this is something which is unique in the Antarctica. It is not found in any other part of the world. Only in Antarctica we find such conditions. Now, next question is, why only in Antarctica? Next is, why only in Antarctica? Why in Antarctica? Because in Antarctica, in Antarctica, two things are important here. One is the geology of Antarctica, and surface configuration. Surface configuration. Right. Now, why we find it in Antarctica but not in Arctic? We don't find that in Arctic. We find them in Antarctica. Ozone hole is in Antarctica. Every year, ozone hole develops in Antarctica, but not in the Arctic. Not in the Arctic. Now, why such conditions? Why such conditions are there? Geology and surface configuration. This is the first reason. Now, understand what is geology and what is surface configuration. If you take the Antarctica, if you take Antarctica, and if you take Arctic, we'll find the variations are: Antarctica is a continent. Antarctica is a land area. It is land area. And above the land, we find ice deposits are there. Ice deposits are there. And this entire area is surrounded by water body. Entire area is surrounded by water body, that is ocean, and I am referring to the Southern Ocean. This is Antarctica. If you take Arctic, the geology of Arctic is totally different. So if you see the geology of Arctic, in the Arctic region, it is having a sea or ocean. It has an ocean, and above the ocean, we find ice deposit is there. Ice deposit is there. Ice deposit is there. Then this entire area is surrounded by land. Surrounded by land. That is continent. Continent area. Continent area. Right. So here we find the land and water contrast are not the same. So here we find land is there, water is there, again land is there. So land and water contrast. Land and water contrast of Antarctica is different from the land and water contrast, land and water contrast of Arctic. So it is water bodies. Within that, the land is there, and then above that, ice is there. So in Arctic, we find more land and water contrast. Land, water, land. Land, water, land. So more contrast are there. And because of this, we find the temperatures in the Antarctica is very low during the winter season. So hence the temperatures in the Antarctica are very low or colder than Arctic. Arctic in the winter season. In the winter season, because of the land and water contrast. In geography, you have studied that land warms also very faster and cools also very faster, and that also makes an impact on the pattern of winds which are blowing there. Winds which are blowing there. So hence we find in the context of Antarctica, the land and water contrast is not same as what you find in Arctic. So hence Antarctica is always seen as more colder than that of Arctic. It is something like this. Arctic in the winter season, it can reach to minus 50, minus 60 degrees centigrade. But Antarctica has capacity to reach minus 80 degrees, minus 90 degrees, etc. Minus 80, minus 90 degrees. So because of its geology and surface configuration. So this is one reason. This is one reason. Geology and surface configuration of the Antarctica is different from that of Arctic. And the second reason is why we find the ozone depletion only in Antarctica rather than Arctic is it is due to certain meteorological activities and chemical reactions. Due to certain meteorological activities and chemical reaction, meteorological activities and chemical reactions. Right. Now what is the meteorological reaction and what is the activities and reaction we are talking? So meteorological activities are associated with the first one is called as jet stream. Second one is polar vortex. Polar vortex. And the third one is a type of a cloud called as polar stratospheric cloud. Polar stratospheric cloud or PSC. Polar stratospheric cloud or PSC, or it is also referred as nacrous cloud. Nacrous cloud, or it is also referred as mother of pearl cloud. It is also called as mother of pearl cloud. All the three names are there. So the role of these The role of these create a special meteorological activities only in Antarctica, which is not seen in any part of the earth. And they accelerate the chemical reaction, and this chemical reaction where they release the chlorine during the month of August, September and October, and that chlorine, which is highly reactive during the month of that August, September, due to the temperature parameters, its reactivity increases, and that is where it breaks the ozone molecule more than any time of the earth, sorry, any time of the year and any place of the earth. And hence, during that phase, the ozone depletion becomes maximum in the Antarctica. Antarctica. Now we'll try to decode them in a systematic way. The first one is jet stream, then polar vortex, then polar stratosphere. Right. So we'll try to understand these three terms. These three terms. Right. So the first one is the jet stream. Jet stream. So now the moment when we say jet streams, what are jet streams? So jet streams are geostrophic winds. They blow at great height. They flow parallel to the isobars. So jet streams are geostrophic winds. That means they flow parallel to the isobars. Parallel to isobars. They keep on rotating along the earth. So these jet streams, if they are strong, these jet streams, if they are strong, they follow straight path. They follow straight path. Straight path. Now, if the same jet stream, it if it becomes weak, a weak jet stream. So rather than following the straight path, it starts developing big loops. So this jet stream, it starts developing big loops. And these loops are nothing but Rossby waves. Rossby waves. And this you are done in your geography. Large meanders will be there. Big loops will be there. We refer them as Rossby types. Rossby types. So jet stream, if it is strong, it will follow the straight path. If it is weak, then it will have a long loops called as Rossby waves. Right. This is one. Now next is something called as polar vortex. What is polar vortex? Polar vortex. So polar vortex is, if you take this as an earth, we find North Pole and South Pole is there. So this is North Pole and this is South Pole. At the ground, you are having high pressure. At the ground, you are having high pressure. But when you move on to the height, above the surface, at height, say around 20 kilometers, there we find a cold wind is there. Now in physics, vortex or vorticity means rotating. Vortex or vorticity means rotating. So here at the great height, we find the cold wind is rotating above the North Pole and South Pole. So we find the cold air which is rotating with low pressure center. And this cold wind, which is found above the North Pole and South Pole, is referred as polar vortex. Right. So we find they are in the north and south. Then the third one is referred as polar stratospheric clouds, PSC. Now, as the name suggests, stratospheric means it is found in the second layer of Earth's atmosphere. So this is called as troposphere and this is called as stratosphere. So in the stratosphere, this cloud is formed. Polar stratospheric clouds. Now understand its characteristics. This polar stratospheric clouds in the second layer of the Earth's atmosphere. It does not provide any rainfall. It is non-rain bearing clouds. No rain is associated with that. No rain. It will not provide any rain. It is non-rain bearing clouds. And this polar stratospheric clouds develops. It develops only during winter season. Only during winter season. And that too, a condition is there. Condition is when the temperature is below minus 78 degrees centigrade. When the temperature is below minus 78 degrees centigrade, then only this polar stratospheric clouds are formed. When it is minus 78 degrees centigrade, then only the polar stratospheric clouds are formed, or else it will not. If it is minus 70 also, it will not form. If it is minus 60 also, it will not. So this is the threshold. This is the threshold only and only if it is below minus 78, below minus 78 degrees, then only the polar stratospheric clouds are formed. That is during the winter season. During the winter season. So remember these three names: jet streams, polar vortex, and polar stratospheric clouds. Right. Now, if you see them through the images, so this is what referred as polar stratospheric, polar vortex, the cold air, and the jet stream which surrounds that polar vortex, jet stream which surrounds the polar vortex. We find them in the North Pole, we find them in the South Pole, both areas. So this is polar vortex and this is jet streams. Now, understand polar stratospheric clouds. See, simple. Polar stratospheric clouds are conditional clouds. They are conditional clouds. They develop only in the winter season. Where? In the troposphere. Only when the temperature falls below minus 78, or else they will not form. Or else they will not form. Minus 78 is the benchmark. If it is minus 80, they are forming. If it is minus 90, they will form. If it is minus 70, they will not form. Only when it is less than minus 78, these polar stratospheric clouds will form. And these clouds, they do not have capacity to provide any rainfall. They are not rain bearing clouds like cirrus, cumulostratus, or cumulonimbus. They do not have rain bearing capacities. They do not provide any rainfall, and they are formed only during the winter season. That too when the temperature is minus 78 or less than that. This is something called as PSC, polar stratospheric clouds. Now understand a bit more on that. So polar vortex and jet stream. Now I told that jet stream can be two types. It can be strong jet stream, or the jet stream can be weak. Now if the jet stream is strong, then it will try to follow the straight path like this. Straight path. But if the jet stream is weak, then what it will do? Instead of following the straight path, this jet stream will move towards the vertex and comes out. Moves towards the vertex and comes out. Moves and comes out. This is how the jet stream behaves when it is weak jet stream. When it is weak jet stream. Is this point clear? When it is strong jet stream, it will act like a boundary for polar vortex. So the strong jet stream, it is acting like a boundary. It will consolidate the polar vortex. It will consolidate polar vortex. It will not allow the polar vortex to spread. So polar vortex will not spread. Polar vortex will not spread. Why? Because the jet stream is like a boundary, confined, and within that the polar vortex is there. But if the jet stream, when the jet stream has become weak, will it consolidate the polar vortex? Can anybody answer me? If the jet stream is weak, when the jet stream is weak, can it consolidate the polar vortex? It will spread. It will not consolidate. So when the weak jet stream is there, so it will make the polar vortex to spread. Polar vortex to spread. So one area where the cold wind is consolidating, one area where the cold wind is spreading, cold wind is spreading. One area the cold wind is accumulating. One area the cold wind is spreading. It is moving. Now, where do you find the temperature can drastically decrease? In this, where the jet stream is strong or where the jet stream is spreading? Where do you find the temperature can decrease to very low? Where the jet stream is strong or where the jet stream is spreading? Where do you find the temperature falls to very low? Very low. So when the jet stream is strong, it will not allow the cold wind to spread. Then the temperature of that air starts to decrease. So perfect, perfect. So here when the jet stream is strong, then the temperature decreases. Temperature decreases. And this temperature decreases drastically. Drastically. Right? So when the jet stream is strong, the temperature decreases drastically. So this is basics. Now we'll apply this in the Arctic and Antarctic. We'll apply this in the Arctic and Antarctic. Now, this condition of jet stream, because of the topography, because of the characteristics of Arctic and Antarctic. In the Antarctic region, because of land water contrast, the jet stream is strong here. The jet stream will be strong in the Antarctic. And in the Arctic, because of the land and water contrast, the jet stream is weak. The jet stream is weak in the Arctic region. It is strong in the Antarctic and it is weak in the Arctic region. Understand? Jet stream here, it is weak, and here the jet stream will be strong. Jet stream will be strong. Weak jet stream and strong jet stream. So here we will find weak jet stream, and here you will find strong jet stream. Up to this, is it clear? Weak and strong jet stream. Now what happens? What happens when they does? When they does? So this is the condition which you find in the Antarctica. And this is the condition which we find in the Arctic, where the jet stream is weak and unstable. And here the jet stream is strong and it is stable. Now, if you take these two areas, in the Antarctica, as the jet stream is strong, consolidation of polar vortex is seen. So this polar vortex consolidates. And here this polar vortex, it is difficult to consolidate. The warm air moves inside and the cold air moves outside. Cold air moves outside. So this cold air which is contained in the strong jet stream, the temperature of this in the winter season, the temperature of this in the winter season reaches to below minus 78 degrees centigrade. Below minus 78 because of its topography. In the Arctic area, because of wavy nature of the jet stream, as the ice is melting and other factors are there, the jet stream is weaker. And this jet stream during the winter season, the temperature of the polar vortex in the Arctic also decreases. It can reach to minus 50 or minus 55 or minus 60. Not lower than that. It can reach up to minus 50, minus 60, etc. But not beyond that. Not beyond that. Now, in this condition, if you take the winter in the Arctic and Antarctic, where do you find the strong possibility of development of the polar stratospheric clouds? In the Antarctica or in the Arctic? Where do you find there is a strong possibility of developing the polar stratospheric clouds? Right. So it is Antarctica. 90% of your explanation is done here. So hence, because the temperature is minus 78, so there is a strong possibility of development of the polar stratospheric clouds in Antarctica. Right? It is not developed, or rarely once in 20 years it can develop, but not always in the Arctic. Not always in the Arctics. Is it clear? Now, this is sometimes when they ask, why do you find the polar stratospheric clouds only in Antarctica? Because of the jet stream, because of the geology, strong jet stream, and the geology, that is land area covered by ice and surrounded by the water. So that makes the temperature to reduce to less than minus 78, and this in turn is responsible for development of the polar stratospheric clouds in the winter season in the Antarctica. But we don't have the conditions in the Arctic, so hence we don't have the polar stratospheric clouds in the Arctic. So Antarctica has strong jet stream during the winter season. Strong jet stream during the winter season, whereas in the Arctic, the jet stream is wavy. It develops the Rossby waves. Rossby. So hence the cold air moves out of Antarctica and warm air reaches to Antarctica. And when the warm air reaches to Antarctica, sorry, the warm air when it reaches to Arctic, then will it enhance the melting of the glacier, or it will make the ice to recover when the warm air is entering into Arctic? When the warm air is entering into Arctic, will it makes the Arctic ice to enhance melting or increase the deposit here? It enhances. That is what happening in the present scenarios. That is what happening in the present scenarios. So the role of jet stream, which is becoming meandering, is making melting of the Arctic glacier more faster. Now, this is referred as which type of feedback mechanism, positive or negative feedback mechanism? The jet stream, which has become meandering and making an impact on the enhancing of the melting of the glacier in the Arctic region. Is it creating which type of feedback mechanism? Which type of mechanism? Perfect. It is positive feedback mechanism. Positive feedback mechanism, that is one event is accelerating. So that's why if you are reading current affairs, you always see that the melting of the ice in the Arctic is far more than that of Antarctica because of such factors. One of them is the role of jet stream. Role of jet stream. Is it clear? So this is how current related things are seen. So the cold winds of Arctic is spreading to the mid latitude. Cold winds are spreading maximum to the mid latitude. Is it clear? So here remember that perspectives. Now when we talk about the Rossby waves, remember Rossby waves means more loops, enhanced loops. This is the strong jet stream. Rossby waves means rather than moving with the latitude, it moves with the longitude. We refer them as Rossby waves, where they develop the long loops. See, don't get confused. Don't get confused. So when we talk about Hadley cell, Ferrel cell, and polar cell, they are totally different from polar vertex. They are totally different from polar vertex. Now, when we talk about Hadley cell, Ferrel cell, and polar cell, this is equator. So here you are having Hadley cell in both areas. You have Hadley cell, and then after that you are having Ferrel cell, Ferrel cell, and then you are having the polar cell. You are having the polar cell. And here remember that these are the patterns of winds which you find here, the winds meeting here and reaching up. This is called as Hadley cell. In the Ferrel cell this is something like this, right? And in the polar cell it is reaching here, moving here, and moving down. And this polar vertex is not a part of that. This is polar vertex which is not a part of that. Is it clear? So this is something which you have done in your geography, and I'm just reconnecting that: Hadley cell, Ferrel cell, and polar cell. So don't confuse with this. These cells are different from polar vertex. So these are the polar vertex what you are reading, and this polar vertex is very well developed in the Antarctica due to special characteristics I told, meteorological characteristics, and also the surface topography. Is it clear? So I think Up to this, it is clear. So hence we say strong polar stratospheric clouds. Strong polar stratospheric clouds are formed in Antarctica, but not in Arctic, right? So this is something which half is done. Now we move on to understand that why the depletion is maximum in the month of October and September. Perfect. So this is where the curiosity is, right? So why it is maximum in the month of October and September, right? Now, can anybody tell me in the month of October and September, where do you find the location of the sun? Is it at the equator? Is it away from the equator? Or is it in the northern side? In the month of October and September. October and September. Where do you find the position of the sun? That is south of equator. Now, the moment when it is south of equator in the month of October, south of equator, then can it maintain minus 78 degrees centigrade in the polar vortex in the Antarctica? In the southern hemisphere, when the sun has moved, can it maintain minus 78 degrees in the southern part? It means that it has changed from winter to spring season, where the temperature will not be minus 78. So when the temperature is not minus 78, then this polar stratospheric cloud will dissociate. It breaks. When it breaks, whatever chemicals are there, the chlorines and all, they become chemically reactive in the month of the September and October. And these chemically reactive chlorine and bromine, which are released due to dissociation of polar stratospheric clouds, enhances the ozone depletion in Antarctica. And that is where the huge amount of ozone depletion is found in Antarctica. As simple as it is. Is it clear? So that's why we find the ozone depletion is dominant in the Antarctica during the same months. Is it clear? Now we'll put them into proper way. So this is polar vortex, polar stratospheric clouds, and jet streams. I hope all three are clear. So the ozone depletion in Antarctica are linked with factor 1, polar vortex, factor 2, roll of jet stream, factor 3 is polar stratospheric clouds, that is minus 78 degrees centigrade or less than that, less than that. Is that clear now? This is something which you have to be keeping in your mind. Now entire process, this is when the jet stream is weak. When the jet stream is weak, the polar vortex will split. And if the jet stream is strong, we refer that as stable polar vortex. And the stable polar vortex will help in the formation of what we refer them as the polar stratospheric clouds, which is seen in Antarctica. And such conditions we find in Arctic. Such conditions we find them in the Arctic. Is that clear? Polar and Antarctic, Arctic and Antarctic. Now, consolidation of whatever we have told. Consolidation of whatever we have told. Now, in the context of Antarctica and Arctic, in both the areas, we find the polar vortex are there. It is always present throughout the year. The polar vortex is present throughout. We find the polar vortex is present. It is present throughout the year. In the Arctic as well as Antarctic, the polar vortex throughout the year it is present. Throughout the year it is present. But when the apparent shifting of the sun moves, when the sun makes apparent shifting from March, that is April, May. So we find summer season is there in the northern hemisphere and winter season will be there in the southern hemisphere. In the southern hemisphere, because of geology and surface configuration, because of geology and surface configuration, we find this will create extreme winter condition. Extreme winter condition where? In the south. Now, when it reaches to June, July, here we find along with that, we have jet stream, strong jet stream. And this strong jet stream makes the consolidation of polar vortex. Polar vortex. And this consolidation of polar vortex, when it is does, all the pollutants which were carried by the winds, like chlorine and bromine, the winds which have carried in other parts of the world where chlorine and bromines are there. So these winds will carry chlorine, bromine, CFC to the both Arctic as well as Antarctic. Now, when the polar stratospheric clouds are formed, so these chlorine, bromine, CFCs will be attached in that cloud. So this cloud, this polar stratospheric clouds are formed when the temperature reaches to minus 78 degrees. Minus 78 degrees in Antarctica. When it is minus 78 degrees, it will create the polar stratospheric clouds. That is in the month of June and July. Now, the sun makes apparent shifting downward. When the sun makes the shifting downward, that means it is moving towards the southern hemisphere. When it is moving towards the south, then the temperature of the south slowly increases. Then the temperature of south slowly increases. Now, as the temperature of the south increases, then the Antarctica, Antarctica also the temperature increases. And this increased temperature will not keep minus 78 degrees centigrade. So that will make a dissociation of the polar stratospheric clouds. So in Antarctica, the dissociation of the polar stratospheric clouds is done. The polar stratospheric clouds will break. So when the polar stratospheric clouds breaks, it will release the chlorine. It will release the chlorine, bromine, etc. And these chlorine and bromine, they are highly reactive at this time. They have highly reactive. During this month, that is September and beginning of October, during this time, they are highly reactive. And these chlorine, they break the ozone molecule. And during this month, we find ozone hole is developed in Antarctica. Ozone hole is developed in Antarctica. And by the month of December, the reactivity of chlorine and bromine stops and it recovers by the month of December. Whatever ozone hole which is done, it recovers by the month of December. By the month of December. And this entire process is seen only in Antarctica, but not in other part of the world. Not in other part of the world. And this is called as the ozone depletion or ozone hole of Antarctica. Ozone hole of Antarctica. Is it clear now? So when we talk about this, whenever when you are reading them, link them with your topics. And I have tried to explain this with your global warming, climate change as well. Right. So what is polar vortex? What is the chemical depletion? What is the ozone hole? Whatever I have explained, I have given. Please read them in your free time. Plus, plus, the process begins from May. Visualize the apparent shifting of the sun to the north and south. Development in the August and highest during the early month of October. Why? Because dissociation of PSC when the sun is shifting downward. Minus 78 will not be there, which brings the chemical change that promotes the chemical activity of chlorine and bromine. And this activates the ozone depletion in Antarctica. And subsequently, it disappears by the month of December. Is that clear? By December. Now, whatever I told, it is explained here. Definition wise, counter the polar vortex, polar stratospheric clouds, everything is there. CFC accumulates in the polar region because of the winds. The winds carry them, high altitude winds carry them from the tropical areas and they accumulate in that regions. So they all accumulate and concentrate when the clouds are formed. That is, polar stratospheric clouds are formed. They are carried by the winds and accumulate when the cloud formation is done as a condensation of the nuclei, right? And I have explained the entire part, strong jet stream and all. I mentioned all these. Please read them carefully. Read them carefully, right? And now we can have a break of 10 minutes. So we'll start the class at 5:05. Is it okay? So can we start the class at 5:05? Or yes, so we can start the class at 5:05. And then as usual at 6 you can have a break of 20 minutes. At 6 you can have a break of 20 minutes. I hope it is clear now. It's a very complex topic, but yet I have given all the explanations, and I try to explain that as simple as possible with my or within my knowledge based parameters. So please read them and consolidate them. Okay, welcome back after a break. So hope I'm audible as well as visible to you all, right? Done. So uh, chlorine and bromine, Gia, they are reactive in the month of September because of ideal temperature. So the reactivity increases at certain temperature. When the temperature is very low and when the temperature is very high, then the reactivity will not be that effective. So the ideal temperature is seen during the month of that October. So due to that ideal temperature, we find we find that it is maximum depletion in that. So during that September, and in the month of December, as the temperature increases, the reactivity decreases and it stops destroying the ozone. It recovers by the month of December. And then uh, stable month in the October, you are talking about ground surface. Fayaz, this is high altitude, not on the surface. It is at altitude. So where do you find 25 to 30 kilometers above the ground? Ozone layer, don't confuse the ground surface with above. We are talking about the altitude mechanism, not the surface mechanism. Is that clear now? Done. Now, next is factors affecting ozone depletion. As I told that it is man-made factor, right? Man-made factor which is dominant. It does not mean that the natural factors are not affecting. Certain natural factors are also there. Certain natural factors are also there. The first one is ozone depleting substances. Ozone depleting substances like chlorofluorocarbon, chlorine, bromine, etc. Right? Then natural factors like volcanic eruption. The volcanic eruption in 1991 released a large amount of the gases, large amount of the chemicals which affected the ozone depletion, and also Chile 2015. Now, if you are reading your current affairs regularly, in the month of January 2022, there was a large amount of the volcanic eruption which took place in the Pacific Ring of Fire. And this made a historical volcanic eruption. And this is a phreatic type of explosion. It is a phreatic explosion which was seen in the Pacific Ocean. And the volcanic eruption was so strong and violent that the gases and the water vapor the gases and the water vapor which is released by the volcanic eruption, they reach to the second layer of the earth's atmosphere. So they reach to the second layer of the earth's atmosphere. The volcanic gases and the water vapor released reach to that layer. Now, which is that volcanic eruption which was in the year January 2022, which made the water vapor to reach to the stratosphere, dust particles to reach to the stratosphere. And because of the volcanic eruption of January 2022, it is one of the reason where the year 2023 the ozone hole in Antarctica was bigger. It is one of the reason where the ozone hole in Antarctica was bigger compared to 2022. And this is the Honga Tonga eruption. Perfect. The Honga Tonga eruption. Right. So it is one of the reason that why the ozone depletion which was recovering has exceeded the previous limits due to the interaction of the Honga Tonga volcanic eruption. Perfect. So hence if they ask, one of the reason is natural factors like Honga Tonga eruption which made the ozone hole slightly bigger than what we find in 2018, 19, 20, 21, 22. It is bigger than that. Natural factors. Then El Nino factors. El Nino factors means it changes the pressure gradient. El Nino means warming of water, and this replaces the cold Peru current by warm current. So when the warm currents are formed, so it affects the pressure gradient, and this pressure gradient will change the wind direction. It will change the direction of the wind. And this direction of the wind which are changed will make change in accumulation of the ODS, change in accumulation of ozone depleting substances, ODS, etc. Right. So this is what you should remember: El Nino and its impact, where it changes the wind direction. And sometimes, if the wind is moving from east to the west, accumulation will be there in the west. Now, when it moves from west to east, accumulation will be there. And during that year, ozone depletion will be maximum in this areas. So this is what we refer that as impact of El Nino, which changes the wind patterns. Right. Then dichloromethane. This dichloromethane is something which is not included in the Montreal Protocol. It is not included in the Montreal Protocol. In the Montreal Protocol. And this dichloromethane is released by foam industries. It is released by the foam industries. More specifically, the countries like China and the countries, even India also, we find more amount of the dichloromethane is released either by foam industry, or sometimes we use them in constructions. And this dichloromethane is a potential threat for ozone. No, it is a potential threat for ozone because it is not included in the Montreal Protocol. It is not included in the protocol. El Nino is different and polar stratospheric clouds are different. El Nino is a pattern of a wind. So El Nino means when the Peru current, ocean current is there, when it is replaced by warm water, we refer that as El Nino. That is totally different. El Nino is downward part, replacement of the cold ocean current by warm ocean current. And polar stratospheric clouds are high altitude. The clouds, don't get confused with them. PSC is different, El Nino is different. So dichloromethane, right? Now, if you see the substances, chlorofluorocarbons, they are found in the refrigerators, air conditioners, solvents, etc. Halogens, they are found in fire extinguishers. Sometimes they may ask in the prelims. Carbon tetrachloride, fire extinguishers, solvents. Methyl chloroform, adhesives, aerosols. Hydrofluorocarbons, we find them in solvents, cleaning, fire extinguishers. So sometimes they may ask ODS and their sources, ODS as well as their sources. In prelims, if they ask, you should be careful in writing them. Now here we come across one convention, one protocol, and one amendment. You should remember: one convention, one protocol, one amendment associated with the ozone depletion. And the convention is Vienna Convention. Just remember, Vienna Convention. Vienna Convention, it is a formalized international cooperation on ozone issue, a framework of policies which were created to protect the ozone layer, to protect the ozone layer. And here it entered into force on 22nd September 1988. And in 2009, it became first convention of any kind to achieve universal ratification. Ratification means officially accepted by all countries, accepted by all countries. So remember, Vienna Convention is associated with the reducing the impact of ozone depletion with framework of laws. Now the systematic work which has been done by a protocol here is the Montreal Protocol. Montreal Protocol. Now Montreal Protocol is something which was adopted on 16th September 1987. It is to reduce or phase out the production and consumption of ozone depleting substances, including CFCs, control and reduce the ozone depleting substances, mainly chlorofluorocarbons and other ODS, other ozone depleting substances, chlorofluorocarbon and other ozone depleting substances. It came into effect in 1989. 1989. And when it was adopted on September 16, every year, every year, we celebrate September 16 as World Ozone Day, International Ozone Day. And this, which was celebrated in the year 2023, the theme was to create awareness among the people about the ozone and how this ozone can be protected. Awareness is understand the significance of ozone, why it is important, why we have to protect ozone, and what methods we have to do to protect the ozone. So this type of awareness is created in every year when we celebrate that with a special theme. And the theme of 2023 is Montreal Protocol, fixing the ozone layer and reducing the climate change. So ozone depletion should also be controlled, plus climate change issue has to be controlled. So twin problems has to be controlled. So that is where the ozone theme was seen in the year 2023. Right now, by 2008, it was the first and only United Nations environmental agreement to be ratified by every country in the world. And among all the conventions, all the agreements of United Nations, Montreal Protocol is referred as most successful. Most successful. It has reached more than 98% of its objectives. It has reached more than 90% of its objectives. It played a very well role in reducing the ozone depletion. Because of the ozone, sorry, because of Montreal Protocol, the ozone is healing. The ozone depletion is reducing. If you take the 1987 and present, we find it has been reducing in its disturbances. And here we talk about a fund called as multilateral fund. Please remember this multilateral fund. And this multilateral fund was established in the year 1991. Now, I told you that any country will get a financial assistance or technical assistance only when it ratifies that convention, only when it ratifies that protocol. Ratifies means officially accepting that in the national laws, officially implementing them through the national laws, amending them and implementing through laws with strict policies. And any country which ratifies any convention or the protocol, they need a financial assistance. They need a financial assistance. And that is where the multilateral fund was created, to make a financial assistance to the developing countries which have ratified the Montreal Protocol and which have made their promise that yes, I'll be reducing the ozone depleting substances in my jurisdiction, but you provide me technical assistance, financial assistance. And this financial assistance is referred as multilateral fund. For implementing Montreal Protocol, it provides financial and technical assistance. To whom? Developing countries. Developing countries. All the developing countries? No. The countries which are ratified the Montreal Protocol. The countries which are ratified Montreal Protocol and whose annual per capita consumption is less than zero point 0.3 kg. So those developing countries will get the assistance from multilateral fund, systematic fund. Then this fund is implemented by United Nations Environment Program, UNDP, World Bank, and United Nations Industrial Development Organization. So these are referred as the custodians of the fund. So they take care of the funds. UNEP, UNDP, World Bank, and United Nations International Development Organization. So these are the four organizations which are the custodian of the multilateral fund. Right. Then, now here amendment which has been done to the Montreal Protocol. Now, in a very simple way, understand that after the Montreal Protocol, the idea was to change the CFC, replace the CFC. So in the Montreal Protocol, it was to replace the chlorofluorocarbon, CFC. And with the further amendments, we replaced the CFC. We replaced the chlorofluorocarbon by hydrochlorofluorocarbon. CFC was replaced by hydrochlorofluorocarbon, that is HCFC. HCFC, hydrochlorofluorocarbon. Right. So CFC was replaced by HCFC It worked very well. Compared to CFC, it was very well. So in refrigerators, CFCs was replaced by HCFC. In air conditioners, CFC was replaced by HCFC. But but there was a small factor of chlorine which was associated with ozone depletion. They decided that this chlorine is also making some impact. So why don't we replace that? Why don't we replace that? So hence again amendment was done to that. Again amendment was done to that. And then systematically HCFC was replaced. HCFC was replaced by hydrofluorocarbon. Hydrofluorocarbon. So remember these three names. So HFC was replaced by HCFC and HCFC was replaced by HFC. HFC. Now the result of HFC was very fantastic. This HFC, when they started implementing, it completely worked very well in controlling the ozone depletion. It systematically worked in reducing the ozone depletion, and the results were excellent. Results were excellent. So remember this: CFC, HCFC, and HFC. Chronology, right? CFC, HCFC, and HFC, right? And the report which was given in the year 2018, in the year 2018, it concluded that yes, the ozone hole is recovering. The ozone depletion is recovering. It is recovering. And they found that the northern hemisphere will recover faster. The northern hemisphere will recover faster than the south because of the type of the geological conditions which are there. They say that the ozone in the Arctic and northern hemisphere mid latitude will recover before the mid of 2035, northern hemisphere. But if you take the southern hemisphere, in the southern hemisphere and Antarctica, it will be by 2060. So north will recover faster than the south. Antarctica and all, it will come back to normalcy by 2060 because of the geological characteristics of Antarctica, which are different from what we find in the Arctic. And apart from that, the ozone depletion in Antarctica is very peculiar type of characteristics, where the thickness falls below 100 Dobson units, and it will take some time to recover. It will take some time to recover. Is that clear? So Montreal Protocol. And if you see the changes on the perspectives of that, so slowly we replace that with HFC. Now why HFC, and why is this Kigali amendment? Why is this Kigali amendment? Now understand, HFC worked very well in ozone depletion. It worked very well in ozone depletion, but it has a side effect. HFC has a side effect. The side effect is that it is a potential greenhouse gas. This HFC is a potential greenhouse gas. Now, what is the characteristic of greenhouse gas? If it is a potential greenhouse gas, what it will contribute? What it will contribute if it is a greenhouse gas? If it is a potential greenhouse gas, then what it will contribute? It will contribute to the temperature rise, and the temperature rise, global temperature rise, is nothing but global warming. Global warming. So this will create an impact on global warming. Global warming. So hence, as this HFC is a potent greenhouse gas, so it is working very well for ozone depletion, but other side it is creating global warming, which is one of the major problem, which is far more dangerous than the ozone, which is far more dangerous than the ozone recovery. So hence in the year 2016, it was decided to something called as phasing down production and consumption of CFC. Phasing down. So understand the word. It is not phasing out, phasing down. That is reducing. Phasing down the production production and consumption of 80% of HFC, 80% of HFC in 30 years. In 30 years. That is when it entered into force. Right. So it means that up to 2048, within that 2048, 80% of the hydrofluorocarbon has to be phased down. It is not phasing out, it is phasing down. Phasing down. Why? Because if you reduce the CFC, then it will contribute in something called as the impact of global warming. So hence, it will help in reducing the global average temperature not to exceed that zero point 0.4. If we keep on using the HFC, there is possibility that it can trigger the global warming. So if we phase down that, if we phase down that, then it will contribute in protecting or intervening in the issues associated with the global warming. So hence the Kigali Amendment talks about phasing down. It talks about phasing down the production and consumption of the HFC, which is a potent greenhouse gas. And HFC wonderfully reduced the ozone depletion, but its negative impact is very stronger than that which has been anticipated. So hence we decided to phase out that. Phase out that. We don't know what we will be using, but we are replacing that. For that, we need a technology. We are working on technology, researches will be done, and then hopefully we can bring out something better than HFC. And this HFC, the phasing out of that, which has to be done, is done in phased manner. Not all the countries at one time. It is done with the phased manner, where they have divided the countries into three groups. The first group is the developed countries. The first group consists of the developed economies like USA, UK, and European Union, where they will reduce 15% of 2012 level of HFC, HFC by 2036. Then, then the second one is the second group of countries, emerging economies like China, Brazil, etc. So they will reduce 20% of 21 level of HFC by 2045, and they will start it by 2024, not by 2020, by 24. So this year they will start. So they will start by 2024, and this they have already started. They will start in this month, or sorry, this year. Then the third group of countries, which includes India and all, third group, which includes India, Pakistan, Iran. And the target for these countries is to reduce 15% of 2024 and 26 level of HFC. 2024 and 26% of levels of HFC by 2047. And this they have to start by 2028. This they have to start by 2028. Phasing down. It is not phasing out. So from 2028, we should start phasing. So it means up to 2028, there is no problem. But after that, we have to phase down the HFC. So this is what the Kigali Amendment is. This is what we refer them as the Kigali Amendment. Is it clear? So Kigali, HCFC, HFCs, and all those. Right. Now this is the chart which gives the same thing. Vienna Convention, amendments which systematically leads to HFC, and then it has been controlled. It has been reduced. So if you see the data, the ozone is recovering. Ozone is recovering. But the worst thing was in the year 2023, last year, mainly because of the Honga Tonga eruption. Mainly because of the Honga Tonga eruption and other factors, where the ozone hole was bigger in the year 2023. Right. Now, India and ozone depletion. Now, India is a part of that, and this will help you in prelims. Right. India has, you should be remembering the words carefully. India has phased out chlorofluorocarbons, carbon tetrachloride, halogens, methyl bromide, and methyl chloroform from January 2010. We have already phased out that. Then, currently we are phasing out the hydrochlorofluorocarbon. So CFC was replaced by HCFC. Now we have to replace HCFC. We have replaced HFC. Thought we have replaced CFC, which is already done. Now we are replacing HCFC, are being phased out. Now the first plan of replacing these HCFCs, hydrochlorofluorocarbon, is between 2012 to 2016. So we worked very well in replacing HCFCs, very well. And the second phase, the second plan of replacing of HCFC, it will be it will be in this stage, 2017. It will start from 2017 up to 2024, phasing out of that. Second phase, second phase, and we refer that as the plan, management plan. We refer that as the hydrochlorofluorocarbon phase out management plan. Hydrofluorocarbon phasing out management plan. Hydrofluorocarbon phasing out management plan. And during the stage 2 implementation, these are facts you remember for prelims. Phasing out of HCFC 141B, a rigid form. Now remember, India is first among the developing countries. India is first among the developing countries to achieve the milestone of replacing HCFC 141B. HCFC 141B in the developing countries, where we are working very, very well in phasing out HCFC as well. As well. Right. Now, India's HFC target is not yet started. So we have to start it somewhere later. Right. So we have planned for that also. As a part of the third stage, hydrofluorocarbon phasing out management plan. Hydrofluorocarbon phasing out management plan 3, which will be implemented from 2023 to 2030. Right. And here we will make a very significant impact on reducing the HFCs and HCFCs. Right. Then start India will start controlling of its HFC. India will start controlling its HFC, hydrofluorocarbon, from 2023 onwards. So now we don't have any burden on controlling HFC. We are working on reducing HCFC. So by 2020, 2032, we will be phasing down the hydrofluorocarbon as well. Is it clear? Now, along with that, very factual one is India Cooling Action Plan was there. Now, the idea is that generally we find the heating areas, office premises, house premises, if the temperature is more, then we are using air conditioners. And these air conditioners, by default, they will release a large amount of the CFCs or HCFCs. Now, if we have a proper building architecture where the cooling infrastructures are there, so we will be reducing the usage of air conditioners, and that will help in less usage of air conditioners or less release of the hydrofluorocarbons in the atmosphere. And such types of plannings where Indian government is insisting, maybe in the construction or maybe in other practices, we refer that as India's Cooling Action Plan, integrated vision towards the cooling across all the sectors. Effective refrigerators, 5-star refrigerators, where they will release less amount of the chlorofluorocarbons, etc. Right. Energy efficiency, transition, energy efficiency, all those. So by this we can reduce the emission of the HCFC, and also we can take a very strong effect on the usage of electricity as well. So we will be working on global warming perspective, reducing electricity, increasing the efficiency, and decreasing the carbon footprints. Along with that, the chlorofluorocarbons or HCFCs which are released during the process has to be substantially decreased in that. So this is called as India's Cooling Action plan. So if you remember this, that is more than sufficient in the context of ozone depletion with reference to India. And if anything you are reading in current affairs, you add this when you get in the later stage, right? Now, the previous year question which was asked, consider the following statement: CFCs known as ozone depleting substances. Ozone depleting substances, right? Now, where do you find them? Can anybody answer that? Ozone depleting substances in the production of plastic foams, in the cleaning certain electronic components, in the production of tubeless tires, as pressurizing agents in the aerosols. Right? So we find them in all the fours. We find them in all the four. We can find them. All four we can find them. All four we can find them. Now, second question is the formation of ozone hole. This is the question which was asked in UPSC prelims. The formation of ozone hole in Antarctica has been cause of concern. What would be the reason for formation of ozone hole in Antarctica? Fast, anybody can mention this. I have explained entire concept. An entire concept is asked in one statement. Entire concept. Read that and try to answer. The formation of ozone hole in Antarctica region. What is the reason for the Antarctica ozone depletion? Read the statements and try to mention them. Read them, use the words appropriately and mention them. See, I'm not telling that all the statements are wrong. These statements are correct, but among them you have to select the appropriate one. The statements mentioned are not wrong here. You have to select the appropriate statement. You have to take the appropriate statement. Perfect. So many are answering which are very perfect. So here you should remember the terms: polar front, that is jet stream, then stratospheric clouds. What are stratospheric clouds? PSC, polar stratospheric clouds. Then inflow of CFCs. Simple. So B is the right answer. The global warming is there, but that in turn creates some mechanism. So not all the statements are wrong here. The statements are correct. You have to select the best among them. Right. Then, which one of the following is associated with controlling and phasing out of ozone depleting substances? Ozone depleting substances. This is very simple and factual one, right? So Montreal Protocol. Perfect. Okay. So we completed a dynamic topic called as ozone depletion. We completed the ozone depletion, right? A very dynamic one, which talks about concepts of geography, a complex phenomenon, and something which are linked with the current affairs as well. So all were included in this ozone depletion perspectives. So very dynamic in the nature. Now next we move on to something called as global warming and climate change. Still more interesting compared to that. Global warming and climate change. Now if you see the present world, if you take the present world 2024, that is present world, the world is facing three major problems. The world is facing three major problems. The first one is referred as the climate change issue. Climate change. The second major problem that the world facing today, apart from climate change, is loss of biodiversity. Loss of biodiversity. Diversity. And the third major issue associated with the world is land degradation and desertification. Land degradation and desertification. So these are the three major problems which the present earth is facing. Degradation means where its productive capacity decreases. Degradation means a sick person, like where its productivity decreases. Always remember, when we say degradation, it means that the productivity decreases. The land is not providing its benefits what we expect. So its productivity decreases. productivity decreases. Right. Now, when the productivity of land decreases, what issues can be seen? Very fast. If the productivity of land decreases, then what type of problems we will be facing? Anyone? Any one problem associated with land degradation? Perfect. Food security will be the problem. Food security will be the major problem, which can be seen as one of the major context. Right. So this is what you have to understand. So land degradation, desertification, deforestations, all these are making a huge pressure on the mother earth. And that is where our ecological footprints are increasing very high. And we have to understand all that with reference to something called as global warming and climate change perspectives. Right. So we'll try to analyze that. The first one is we always come across global warming and climate change, right? So most of the times we combine global warming as same as climate change, but there is a difference between these two words. Both are not the same terms. There is a difference between that. So when you read the climatology, when you read the climatology, we have elements of climatology which are studied, fundamental elements of climatology. And these elements of climatology are something called as winds, precipitation, that is rainfall, pressure, moisture, etc., etc. So we refer them as elements of climatology. So that's why when you read climatology, we study the temperature, winds, precipitation. You can add temperature also, temperature, winds, precipitation, etc. Increasing temperature, decreasing temperature, variation of temperature horizontally, vertically. So all this you study in your climatology. Right. Now, when these statistics, when they are recorded, when the statistics of these data, when the statistics of these data, when they are recorded for a longer period of a time, say 20 years, 30 years, then we refer that as climate. We refer that as climate. And the same data, if it is recorded for a shorter period of a time, we refer that as weather. We refer that as weather. When it is recorded for a shorter period of a time, we refer that as weather. Now, when these data which are recorded for a long period of a time, the data which are recorded for a long period of a time, when these data change, when these data show some changes, which are recorded for 20 years, 30 years, not 1 month, 1 year, 20 years data, when they show changes, then we refer this as climate change. We refer that as climate change. When the 30 years data are altered. So climate change means when you talk about the temperature, example, temperature can increase also, temperature can decrease also. Change means changing from the normal values. The temperature can increase also and the temperature can decrease also. And if you take precipitation, rainfall, it can increase also, it can show decrease also. So it shows both the tendencies. It will show both the tendencies. Both tendency, that is increasing and decreasing, both will be there. So climate change talks about increasing temperature also, decreasing temperature also, increasing rainfall and decreasing rainfall also. Both are there. Both are there. We refer that as climate change. Right. Now, if you are talking, if we are talking about only the average temperature of earth which is increasing, if you are talking about only the average temperature of earth, average temperature of earth which is increasing, it is not decreasing, only increasing, only one small parameter. If the average temperature of earth which is increasing, average temperature of earth which is increasing, we refer this as global warming. We refer this as global warming. Global warming. Now, can we say global warming is same as climate change? Are both same? Global warming and climate change are both same? No. So what best we can say? What best we can say when we say global warming and climate change? So we say global warming is part of climate change. Global warming is part of climate change. Part of climate change. So hence, whenever when you are writing definition of global warming and climate change, you should be very careful what you are talking. What you are talking. So you can't say that roti curry is same as roti curry is same as what we say bahubali thali. So when you order for bahubali thali or North Indian thali, it will have roti, it will have paneer, it will have all thing, everything will be there. All context will be there. So that is a bahubali thali or North Indian thali. And roti curry means two rotis and a curry. So can we say roti curry same as bahubali thali? No. So that is a part of the thali. And in the global warming, we talk only about increasing of the temperature. We don't talk of decreasing of the temperature. But in the climate change, it can be increase, it can be decreasing as well. So henceforth, whenever you are writing your definitions, please remember that climate change and global warming. So global warming is a part of climate change, which talks about the increasing of the average temperature of the earth. Is that clear? Now, global warming and climate change. Now, next term is something called as greenhouse effect and global warming. Now, what is this greenhouse effect and what is the global warming? Now, when you have studied about the heat budget in the context of geography, you have studied about the heat budget, right? So I don't want to explain that in detail because it will become most of a geography class. Heat budget means where we talk about the calculation of incoming solar radiation insolation and the energy which is released by the earth system, the energy which is released by the earth system. So it is what we are reading about insolation, which is in the form of short waves. Insolation is in the form of short waves. And then what it is reflected or radiated, what the heat is reflected or radiated by earth system, earth system. And when you study this incoming solar radiation and the amount of energy which is reflected or radiated by the earth system, I'm using two terms. One is reflected and second one is radiation. Reflection is different, radiation is different. Reflection is instant phenomenon, albedo. Radiation means when it heats the body, after heating, then the body will start emitting radiation. We refer that as radiation. Reflection is different, radiation is different. To emit the radiation, the body should be heated, and for reflection it does not need any heating. Radiation and reflections are surface phenomena. Ice has high reflectivity. The radiations will not heat the ice, it will instantly reflect. Oceans have high amount of absorption, less reflectivity. Ocean water is heated when the heat enters into the water bodies. So reflectivity is different, radiations are different. So hence, whenever when you talk about heat budget, you should remember the term. It is the amount of the heat which we receive from the sun and the heat which is reflected and radiated back by the earth system. Earth system means we are talking about atmosphere, glacier, and all those. Now, if we take this 100% as the insolation as 100%, then in that we find that around 35% is reflected. I'm using the term reflected. 35% is reflected, reflected by the clouds, atmosphere, and the ice deposits. And this which is reflected is in the form of short waves only, in the form of short waves. It's instant one, and this is called as albedo of earth. This is called as albedo of earth. Albedo of earth. So out of 100%, 35% is reflected. So remaining is 65%. Remaining is 65%. And out of the 65%, 14% 14% is absorbed by the Earth's atmosphere. Absorbed by the Earth's atmosphere. Maybe for photosynthesis, maybe by organisms, maybe by plants, so which is absorbed by the Earth's atmosphere. So out of 65, 14 is absorbed. Then remaining is 51%. So this 51% which is left out will reach to the Earth's surface. This 51% will reach to the Earth's surface. So this is the surface of an Earth. And this 51 units, it heats the Earth. It heats the Earth. And when the Earth surface heats, it will not reflect. It will start emitting radiation. When it is heated, then the Earth will start emitting radiation. And these radiations which are emitted by the Earth, we refer them as terrestrial radiations. We refer them as terrestrial radiations. And the temperature of Earth is comparatively less than that of a sun. So temperature defines the nature of the wavelengths. Temperature defines the nature of the frequency. So insolations are in the form of short waves, and we know that wavelength is inversely proportional to frequency. So they are short waves, but high frequency. But the terrestrial radiations which are emitted by the Earth, so they are having long wavelength. Long wavelength, right? And if you see the Earth's atmosphere composition, the Earth's atmosphere is opaque for long waves. This you have done in your geography. The composition of atmosphere, which consists of many gases. So this atmosphere becomes opaque for long waves. So hence, out of this 51 units, which is in the form of terrestrial radiation, 17% escapes to the space, and 34% is absorbed by the Earth's atmosphere. 34% is absorbed by the Earth's atmosphere. That is terrestrial radiation, and these terrestrial radiations are long waves. Long waves, right? So this is what your geography is. Now understand this. The composition of the Earth's atmosphere consists of solid, liquid, and gaseous particles. Generally we say the gaseous and aerosols. Now if you take the cotton cloth and if you take the silk cloth, if you dip them in the water, both are cloths. Cotton is also cloth, silk is also cloth. If you dip both in the water, which cloth will absorb more water, the cotton or the silk? If you take the cotton and if you take the silk and if you dip them in the water, which one will absorb more water? Even though both are cloth, but cotton will absorb more water. Why? Because of its composition, because of its characteristics. It will absorb more because it is having the potential to absorb more amount of water. Both are the cloths, but still it absorbs more. Now in the same way, when you talk about the Earth's atmosphere, in the Earth's atmosphere we find many gases are there, many aerosols are there, solid, liquid particles are there, many gases are there, many particles are there, which consist of oxygen, which consist of chlorine, which consist of the gases like carbon dioxide, which consist of methane, which consist of water vapor, right? So many such gases are there. Oxygen is there, chlorine is there, carbon dioxide is there, methane is there, water vapors are there. So many such gases are there, which are there in the Earth's atmosphere. Now, among these atmosphere gases, all the gases will not have same absorbing capacity. Some will absorb more and some will absorb very less, like cotton and silk. And here, instead of the water, put that as a heat. Now the heat which is emitted by the Earth, so here we find there are certain gases which absorbs more terrestrial radiation than the other, like the carbon dioxide, methane, water vapor. So these are the gases which are having the capacity of absorbing more amount of terrestrial radiations, which are in the form of long waves, which are in the form of long waves. So these terrestrial radiations which are absorbed more by carbon dioxide, water vapor, methane, etc. So when they absorb the terrestrial radiation, what will happen to their temperature? Their temperature will increase. So their temperature will increase. Their temperature will increase. And the moment when the temperature increases, the moment when their temperature increases, after increasing the temperature, whatever heat which they have accumulated, they will send it back to the earth. They will revert it back to the earth. And this heat which is reverted back by them to the earth, it is the radiation which is hitting them, and they are absorbing, and again they are sending them. We refer that as counter radiation. We refer this as counter radiation. Counter radiation. And this type of the counter radiation, where the long wave terrestrial radiations are absorbed by certain gases like carbon dioxide, methane, water vapor, and they do reflect back, by which the temperature of that area increases. Temperature of that area increases, and we refer this as greenhouse effect. We call this phenomenon as greenhouse effect. Greenhouse effect. And the gases which are involved in the greenhouse effect, we refer them as greenhouse gases. And the gases which are involved in the greenhouse effect, we refer them as greenhouse gases. We refer them as greenhouse gases, right? And greenhouse gases, if they increased in the Earth's atmosphere, greenhouse gases, if they increase in the Earth's atmosphere, what will happen to the average temperature? Will it remain same, or it will increase the Earth's atmosphere? If the concentration of greenhouse gases like carbon dioxide, methane, water vapor, if they increase in the Earth's atmosphere, what will happen to the average temperature of the Earth? Will it remain same or increase? That is what referred as global warming. That is what referred as global warming. So this greenhouse effect, when we apply to entire Earth, this greenhouse effect, when we apply to the entire Earth surface, we refer that as global warming phenomenon. Global warming phenomenon. And this global warming phenomenon is nothing but the average temperature of Earth which is increasing. Is nothing but the average temperature of Earth which is increasing. Now why it is increasing? Because of the increasing of greenhouse gases. Why it is increasing? Because of increasing of the concentration of greenhouse gases. Not all the gases are greenhouse gases. So carbon dioxide, methane, water vapor, nitrous oxide, we refer them as greenhouse gases. So this is what we refer them as insolation. This is short waves, insolation. It heat the earth, and after that, this is terrestrial radiation, which is in the form of long waves. And these terrestrial radiations are trapped here by these substances, and then they are reflected back. We refer this as counter radiation. This is something which increases the average temperature of the earth. Greenhouse effect is the process by which the radiation from the sun are absorbed by the greenhouse gases and not reflected back. See, don't get confused. Greenhouse effect is a process by which the radiations from the terrestrial radiations, because the atmosphere is opaque for long waves, not the sun's radiations. It will absorb, but very less. Long waves are absorbed by that. You just change your definition. Greenhouse effect is the process by which the radiation, that is terrestrial radiations, are absorbed by the greenhouse gases, and reflected back to the earth, not to the space, reflected back to the earth. Is that clear? Atish, is that clear? Greenhouse effect is the process by which the terrestrial radiations of the earth are absorbed by the greenhouse gases and reflected back into the earth. Reflected back to the earth, we refer them as counter radiation. We refer that as counter radiation. So just modify your definition. Is it clear? So we refer this as the greenhouse effect and global warming. Is that clear? The definition what you have written and definition what I told, just make clarification in that. Right, so hence it is the increasing in the concentration of greenhouse gases which is making the global average temperature to increase here. And if you take the data, if you take the datas, so in 2020 when we calculated the data, the greenhouse concentration has reached to very high level. So these are always calculated in parts per million. ppm means parts per million. Parts per million, right? So we find that the level of carbon dioxide were 413 parts per million. 413 parts million. And methane was 100 and sorry 1889 parts per billion. And nitrous oxide is 332. So compared to 1750, we find there has been a tremendous increase in carbon dioxide. So the carbon dioxide has increased to say 149%. Then the concentration of methane, which has increased to 262%. And the concentration of the nitrous oxide has increased to 123%. 123%. So it means that the greenhouse gases which have increased, they're absorbing more amount of terrestrial radiation and they are developing the counter radiation, which in turn is creating the huge impact on the earth's average temperature. We refer that as global warming. And if you see the data, so this is what the definitions I told: counter radiation, greenhouse effect and all. So please read that after the class. If you see the data, if you see the data, since 1906 global average temperature has increased to zero point 9 degrees. 1906. And the annual global temperature would exceed to 1.5 degrees above pre-industrial level. Now here, the moment when we say pre-industrial level, you should fix the year here. Pre-industrial means it is 1850 to 1900. So this year between 1850 to 1900 is referred as the pre-industrial level. Pre-industrial level 1850 to 1900. 1900. And it has anticipated that it will exceed beyond what we are making. Right now, it has diluted, it has been expressed by the usage what we are doing. So when we talk about this coal, crude oil, natural gas, if you see the data, this is something about the coal. And if you take the next one, which talks about the natural gas, so this is natural gas. Natural gas, this is coal. This is coal, right? So if you take this is crude oil. Crude oil. So the consumption of coal, crude oil, consumption of coal, crude oil, and natural gas has increased. Now these gas are referred as which types of the fuels? The coal, crude oil, and natural gas. They are referred as which types of fuels? Coal, crude oil, and natural gas. We refer them as fossil fuels. So the fossil fuels has increased. The consumption of fossil fuel has increased. And this fossil fuel is generally because of man-made activities. Generally because of man-made activities. So hence, who is the major culprit of global warming? They say man. Major culprit of the global warming is man. So hence we say the present global warming is anthropogenic. Anthropogenic. That is man-made. That is man-made. Now just make an analysis of this. We can have a break of say 20 minutes and we will start the class at 6:25. We'll start the class at 6:25. Is that clear? So this is how you try to put all the understanding in this class so that the further discussion will become easy for you to remember that, right? So we'll meet up at 6:05. Right. So just go with this counter. This is all your geography. This is all your geography. I just explained that in a simplified formats. So we'll meet at 6:25.
ಕೊಡಿದ್ರೆ
Hmm.
ಕನ್ಫರ್ಮ್